Okay, so I keep forgetting, but this time I decided to write it down so that I remember to tell you that most of the course is based on this book by Peskin and Schroeder, and on two sets of online notes. So you can find them online by John Preskill and David Tong. This is a course that Preskill taught on QFT. He has many other lecture notes on many other subjects, but we're going to follow the QFT course. And David Tong also taught QFT in part 3 in Cambridge. So you can also find the notes online, okay? So last time we spent, well, yesterday we spent most of the time quantizing the Klein-Gordon theory, and we found that this is the form of the fields, and that we could interpret A and A dagger as annihilation and creation operators, respectively, and they satisfy the standard commutation relations. Okay, so here, thank you. Okay, so yesterday we ended the lecture by worrying about causality. And we made the claim that perhaps any operators which are functions of our field phi should be observables. But for them to be observables, they had to satisfy a very important requirement, which is that any two of such observables must commute if they are space-like separate. Otherwise, we could transmit information faster than light, than the speed of light, and that would violate causality. Of course, if these are functions of phi, all we have to check for this to be true is that the fields themselves commute whenever this is true. Now, following Andres' observation.
No, I just want to ask something. I mean, imposing the commutation of two observables when they're space-like separated is not too restrictive. I mean, what about if I just require that the correlation functions constructed with this sort of operators are zero at space-like separation? Because that will imply that I have no way of making a measurement here that affects a measurement here.
Well, in fact, we're going to find that this commutation relation, well, you want the correlation function on any states to be zero there, right?
Right.
So if it's true for any states, then it's true as an operator statement. Right? Imagine you have a matrix, and you say that every entry of the matrix is zero. So that's the same as saying that the matrix is zero. Yes.
Isn't this statement not true for ordinary quantum mechanics? Like that, if you just think about two observables, like making two measurements at space-like separation,
in regular quantum mechanics, there is no reason why you couldn't imagine doing that, right? There is no relativity that you have put in. Okay, very good. But now, following Andres' observation from yesterday, right? Remember, we started the whole theory by imposing that this was true at equal times, right? So if we could prove that this is Lorentz invariant, then by a Lorentz transformation, we can bring any space-like separation. So imagine this is our point X, and this is our point Y. There is always a frame where these 2 points happen to have equal time. Okay? So in principle, all we have to do is to show that this is Lorentz invariant, which is non-trivial because in the quantization process, we did something very violent to Lorentz invariance because we treated time and space in very different ways. In fact, time was something very important for us, while space was playing the role of just a parameter, or a set of parameters. Now, in order to do this, let's actually try to carry out this. Sometimes it's convenient to write this as as the sum of 2 objects. This object is the first one, and this object is the other one. Okay. Here, this is plus and minus, or you can think about one of them. In fact, one of them is the dagger of the other one, right? So we could also think about that, but it's just a very standard notation. So if we have that, this commutator becomes, we start with 5 minus x, 5 plus of x, 5 minus of y, plus 5 plus of y. Clearly, the minus minus commute and the plus plus commute. Therefore, this is just 5 minus of x with 5 plus of y plus 5 plus of x, 5 minus of y. Okay? Very good. So let's compute one of them. Let's say the first one. Well, let's use what the formula tells us. So we have for the first one, d3k over square root of 2 omega k. For the second one, let's use k prime. Okay, and then we have e to the, so for the first one, we had a minus. So we have minus, sorry, am I using the right convention or the? Yeah, there is something wrong. Well, this is just a convention, so it shouldn't matter. Okay, so if we keep going, we have E. Yeah, it's, no, it's, okay, this is just, yeah, that's fine. It's just, I think this is the convention that I used yesterday, wasn't it? Okay, so it's a convention. So the important thing is that in the same set of lectures, you should never be inconsistent. But other than that, if you use the same convention, it doesn't matter. Okay, so we're going to have for phi minus, we have minus I k dot x. And coming from phi plus, we have plus I k prime of y. And now we have the commutator of ak with, this was with a dagger k prime. Okay. But this commutator is nothing but according to what we have there, is a delta function that logs k and k prime. So we can carry out one of the integrations, and we get an integral d3k of e to the I. So if we do that, the k's, we can put k here, dot x minus y. And here we have 2 times wk. Okay. Now remember, we said that all we wanted to know was whether this thing was Lorentz invariant. Is this Lorentz invariant? Well, yes, it's exactly the object that we constructed, the measure we constructed last time, right? This object can also be written as integral d for k delta of k squared minus m squared e to the minus I k dot x minus y, okay? With a constraint that k0 is positive, because that's the branch we are taking, okay? And this is manifestly Lorentz invariant, so we succeeded. That's great. However, there is something interesting that we can ask.
Wait, how are we taking the positive branch here?
We are defining wk to be plus the square root of k squared plus m squared, right? This equation has two solutions. Well, remember what k means, right? This is k0 squared minus k squared. So we are solving for k0. When we do this integral, this delta function is used to solve for k0. So k0 becomes log to be wk, or that's what we call wk, but only for the positive solution. Okay? So you say, well, we're done. That's great. So there is nothing else to be done. Well, except that, you know, it might be nice to actually check that we got 0.
0 minus m.
Yes. So it would be nice to check that we actually got 0, right? We know it has to be 0 by Andres' observation. But we actually have to make sure that we didn't make any silly mistakes, right? So we can just look at the other formula, phi of a dagger, phi of y, right? So we now have this. And what do we get? So if we do exactly the same calculation, we will end up with a formula that looks like this. Now with y minus x. Okay. Now you see that if you change k by minus k, then you get exactly the same object, and we find a cancellation. Okay. So we found that this is 0 due to a cancellation of two contributions. Okay. Now, is there any physical meaning to these contributions? Well, they better don't have a physical meaning, right? Because we're not supposed to measure them. But is there any meaning that we can even heuristically attach to these guys? So in order to do that, let's actually follow again the suggestion and consider what happens when we take the expectation value of these operators. Say we take this expectation value. What could this be? What could the meaning of this be? Well, from our description that the states produced by AK on the vacuum, at the end of the lecture, we will support that interpretation. But yesterday, we said that this state, as defined by AK acting on the vacuum, had the interpretation of a plane wave of a particle, or something that is basically a plane wave. When you put them together in this combination, then you could think about this as an object or a wave function that describes a particle at point x. Therefore, this object could be understood as the amplitude for a particle to propagate from x to y. Yes?
Sorry, going back a little bit.
Yes.
The cancellation
between the two brackets involve replacing the 3-vector k by minus k.
And then you still have the k0.
But the k0 components, how do they work out? They are not the same, so the two expressions.
Well, we agree that this is Lorentz invariant, right? Well, then go to a frame where the two times are the same. Very good.
Can you explain again why that's Lorentz invariant?
Why this is Lorentz invariant? Well, this is clearly Lorentz invariant.
How we went from the top line to the bottom line?
Well, it's actually easier to go from here to there. Yeah, I mean, this requires inspiration. From here, there only requires skills. So it's much easier to go along the side of a skill. So you just take this, right, and carry out the k0 part of the integration using the delta function. But this delta function has two solutions. So you are supposed to add up over both solutions. And this function kills the solution where k0 is negative. And it gives you 1 when k0 is positive. So when k0 is positive, you get 1 from here. This delta function allows you to do the k0 integration. The Jacobian that you produce is 1 over k0, and you get back to this formula. Okay? Yes?
So it seems like the theta will be certainly Lorentz invariant if you're inside the light cone, but what if you're outside and you can go back and forth across T to 0?
That is true. Last time in QFT0, we said that this theta was actually Lorentz invariant inside the light cone. Now, outside the light cone is true. We can change the sign of k0. But remember, the light cones we're talking about are different light cones, right?
For X and Y.
For momentum and space,
Okay.
right? This is actually momentum. It's a momentum light cone. And here, when we talk about being outside the light cone, we literally mean outside the light cone in coordinate space. Yes?
Particle points X.
Yes.
That's sort of mentioned those.
Yeah, it should be, yes. I mean, I'm not claiming I'm deriving this. I'm telling you this could have the interpretation of something that generates, this field generates a particle at point X. This is not a mathematical statement. It's just some sort of trying to interpret what this could possibly mean. But now you would say, well, maybe this interpretation is a little bit funny, even, because if I take that literally, I would take this literally, and this would mean that there is some. Well, first of all, is this 0 or not? What do you think? If the 2 points are space, the separation is space-like. Is it 0? So who thinks it's 0? Okay, so let's actually see what it is. Oh, please. Well, if we plug the formula, right, with phi minus and phi plus, we see that from this side, phi plus give us 0. So only the phi minus part survives. And from this guy, only the phi plus survives. Right? Is that clear? Of course, we can add 0 to this, meaning we can write this like this. Right? This is 0 because this kills the vacuum and this kills it. This is a double 0. What did I do? Oh, yes, there is a minus. So this is definitely the same as this, but this was the commutator. Or is the commutator, which we just computed over there, and is given by a number times the identity operator. Right? This thing is that integral times the identity operator. So we get the integral we had over there times the identity operator. And this thing is just the normalization of the vacuum, which is 1. Now, you might hope that this is 0, this integral, but it's actually not 0. And it's your exercise. Yes, exactly. At this point, we're only thinking about x and y, space-like separated. And by a Lorentz transformation, let's take x0 to be equals to y0. In fact, equal to 0, say. So this integral is just an integral d3k. It's something that you can imagine. You can just sit down, and I hope you're imagining that very much, because you can imagine sitting down and doing it. It's just this integral, okay? So your job is to compute this integral in terms of Bessel functions. Okay? And then define R to be x minus y, the distance from the point x to the point y, okay? And show that this thing, as you take R to be very large, okay? You want to see if there is something terrible that happens, not even when the points are close. You want to make them far away and see what happens. So your job is to show that this actually goes like this. Yes?
How did you get that last line? Well, why did the 4 vectors in the exponent become 3 vectors?
Because it's Lorentz invariant, right?
Oh, yeah. Okay.
So I can go to the frame where x0 and y0 are the same. And why not? It doesn't, well, they drop from there. Just go to the frame where x0 and y0 are the same.
And we can do the same thing up there for the commutator.
Yes, we could have done it, yes.
Okay.
And remember, that's how we started the whole conversation. We said that if we knew that this was Lorentz invariant, we didn't have to do any computations, because we can go to the frame where they are at equal times, and we started the whole computation by imposing that equal time commutators were 0. That was the starting point of yesterday's lecture. Okay? So we have this thing. So one of the two pieces. So what have we learned from here? Well, what we learned from here is that if we now think about this commutator, which we know is 0, we just proven that it's actually 0 as an operator, so it's 0 sandwiched between the vacuum, is in fact the sum of two terms that are not 0 outside the light cone. And they have interpretations as particles propagating one of them has interpretation as a particle going from y to x, and this one has an interpretation of a particle going from x to y. Yes?
So here, this kind of a correlation function, right? When you calculate it here for large particles, it is okay in space-like separations when you go outside, but it goes to 0, right? Whenever n is...
No, it's actually not okay. It's anything that is not 0 is terrible.
Okay.
But okay, it's not completely insane, but it's not good.
I can relax my condition and just say that if they are infinitely far away between both, then I expect that my correlation function goes to 0, which is this case, right?
Yes, but you don't want an experiment that you do here and one that you do 3 meters or 3 kilometers from here to affect each other if they are done at equal times.
So the thing here then becomes a little bit more like nasty if n is 0, right? If I consider a massless particle.
Well, that's true. That's true. If you're considering a massless particle, then you can run into trouble. But not for this reason, because the only thing that is observable
It's just
are the fields themselves, and they commute. Okay, the cancellation is completely clean. It's absolute. It's just zero. Okay, but now the interesting part is that it's a cancellation. It seems to be the cancellation among two things.
Wait, what? Can you repeat that part about massive particles? What was the?
I mean, Andres is saying that this doesn't look as terrible as it seems. If the mass is very, very large, you would really have to go to very short distances to see any violation of causality, to actually see these particles propagating. But if the mass is zero, this integral seems to give you something that can violate causality at any distances. But I'm saying that it's not even in that case, because the only thing that is important is the commutator, which we have proven to be exactly zero. And it's zero due to a cancellation of two effects. Okay? Now, these two effects, in this case, we are not so dramatically shocked by what this means, because we haven't done this complex scalar case. But trust me, you will. And when you do, you're going to see that this cancellation happens because you have a particle propagating from one point to the other point, and is canceling something that looks like the complex conjugate of that particle. And that object is going to be called an antiparticle. So causality is a consequence of having, for each particle, you must have something that is called an antiparticle, where the antiparticle is defined as something that has exactly the opposite quantum numbers as the particle that you have. Of course, our scalar field is a boring field, it's a real field, so it doesn't have any extra quantum numbers, so it's its own antiparticle. So it had no choice but to cancel among themselves, okay? So we didn't see something striking happening, but I'm telling you, you will see something striking. Yes?
I'm still not sure how this doesn't violate causality. Because if you just have a huge number of particles at x, isn't this saying there's a finite chance probability of one of them tunneling to y? But if there's no particles at y, I don't see what can tunnel back to cancel.
So what I'm trying to say there is that what you can measure, so that's how we started, by saying that the observables are these quantities, these operators, okay? So you could try to measure an operator here by computing some correlation function there, and another one by measuring here. Somebody agrees with you to compute something here, to measure something here. But since the two operators that you are computing or that you are measuring commute, there is no way that they can affect each other, okay? All I'm saying is that from the mathematical description and the interpretation we're giving to these objects, the cancellation seems to happen due to this effect, okay? Is that effect real? Is that something that actually happens? Well, I'll leave it up to you to think about it, okay? I'm just pointing out something amusing, okay? Very good. Now let's go back. So is this something that you should? This is one of the quotation mark exercises. If you want to do it, do it. If you don't want, if you just trust people who has done it, then it's fine, okay? Now let's, for a second, go back. Just for a second, just to remember something we did there and see how it connects to what we're doing here. QFT0, we learned from unitarity that any scattering amplitude, if you had some internal states and some external states here, that any scattering amplitude should have singularities which are poles And those poles had the form of 1 over the momentum of the particle minus m squared plus I epsilon. You remember we got that in QFT theorem. That was one of the main outputs of imposing unitarity. And just from here, we learned many, many other things, which I'm sure you all remember exactly. And if I ask you to reproduce it, you could just do it. Okay. The laugh is reassuring. Okay. Very good. Very good. Okay, Tibra will take care of that. So what is this? After all, we found this when we were imposing that this object was a physical particle propagating from one point to another. So this object is in momentum space. So it motivates to think that in coordinate space, so in other words, if we perform the Fourier transform back to coordinate space, this object could have a nice meaning. Okay? So that's the end of going back to QFT theorem. Now we're back at QFT1, back to the future to QFT1. And we say, well, if these objects have that meaning, or the meaning we are trying to attach to them, of a particle propagating from y to x, and we want to be inside the light cone, okay, so now we have our point x and our point y there. We would like to have an object that has the following meaning. We would like to describe the propagation of a particle that goes from x to y, okay, if x happens before y, okay? And we would like the same object to describe a particle that moves from y to x if y happens before x, okay? So if this is the case, meaning if y0 minus x0 is positive, okay, we would like this to describe a particle that goes from x to y. If by any chance y happens to be here, we would like the object to be given by the propagation from y to x. Okay? Now the claim is that this thing here, well, it's a claim, so it's not a definition, is nothing but the object we found from unitarity. Okay, let's see how much time we have. Okay, we could try to actually prove it. What do you think? Let's do it. Yes, of course, let's do it. You're not the one here in the Why not? We're all excited. Let's fire up. Okay, let's try. So this is a time for one of these jokes. In case we fail. Okay, so what do we want? We want to take this object. Once again, we're going to start from the side that only requires a skill, not the side that requires inspiration. That we leave to Feynman. Okay, so we want to perform this integral. Well, not really the full integral. We want to do the 0th component. Okay, so what do? We take the 0th component. Okay, well, in fact, let's leave everything else outside. So it's an integral from minus infinity to infinity of k0, and we have e to the minus I k0 x0 minus y0. Okay. There is also the other piece, which is minus I k dot x minus y over there. But I don't want to worry about that at this time. This object here, I'm going to write as k0 squared minus k squared plus m squared minus I epsilon. Okay, so this I can factor as k0. Oh, I didn't tell you, but, well, no, yeah, I did, but 3 weeks ago. What is this epsilon supposed to be? Very, very small, right? It's a very, very, no, it's not 0. There is a very big difference between 0 and any small value. Okay. Positive, yes, positive. Very good. Epsilon is very small, but positive. In fact, we can take it to be infinitesimal, meaning that every time we see an epsilon squared, we just drop it. Okay? So when we have this, what do we have? Well, we can call this, let me call it wk squared. So we have k0 is the same as minus, I'm factoring this out, right? So square root of wk minus I epsilon and k0 plus square root of wk squared minus I epsilon. So this thing will give us k minus wk squared. This thing will give us something like plus I epsilon. When you have an infinitesimal, if the 2 times the infinitesimal is an infinitesimal, or a half the infinitesimal is an infinitesimal, so no worries about that. We have k0 plus wk, and then we have minus I epsilon. Okay? We just plug this in here.
What have you done in this step?
Oh, yes. In which step? Sorry?
So you factored this expression and then how?
Oh, I just expanded. This is an infinitesimal object, right? Okay. So I'm just Taylor expanding and saying that an infinitesimal times anything is an infinitesimal. So I'm just calling it epsilon, not caring about any factors. Is that correct?
I mean, if I do the expansion where I should take omega k outside of the square root.
Yes.
Expand it.
Yes.
And I still have some omega squared
Times epsilon, which is an infinitesimal quantity.
Yeah, your omega depends on k. So
okay, you are. Yes.
Your epsilon is killing.
It's an infinitesimal quantity. Anything times an infinitesimal quantity is infinitesimal. Okay? So I should call it epsilon tilde, but I'm not going to bother to call it epsilon tilde, right? It's a new infinitesimal, but I'm not going to bother to actually make the distinction. If you want, in your notebooks, you can now, from now on, keep writing epsilon tilde, which is whatever you get by doing this expansion. So we have I epsilon, k0 plus minus I epsilon. Okay? So what is this integral? Well, as usual, if you have an integral over a real line, you can draw the k0 complex plane. Think about k0 as a complex variable. Why not? I mean, we do this all the time. And the integral is an integral along this contour from minus infinity to infinity. Okay? But this function has poles, right? We should be able to draw where the poles are. So the first one is near WK, somewhere here. But it's not on the real line, it's shifted. It's shifted by so this is the actual location of the pole, right? In this case, we got here, and we shifted here, okay? Now, of course, whenever we see an integral like this, we're very tempted to just use a contour deformation argument and try to evaluate the integral using the poles, okay? But here, this is our integral from minus infinity to infinity, and in order to be able to use these poles, we will have to close up this contour either by going around infinity on the upper half plane or by going around infinity on the lower half plane, okay? Of course,
It's like fan blades. Like you go up this way and then you slide down and then you go up.
yeah, it all depends on the function, but in this case, the natural thing to try first, I mean, in complex analysis, the first thing you try is to close around infinity. If that doesn't work either on the upper half or the lower half, then you try fancier contours, right? But this is the first thing you would try, okay? So now let's look. That's one option, and this is the other option, right? So what can you do? You can say, well, let me check. I would like to choose the contour that allows me to forget about this contribution, right? So I have to look at the integrand and decide when this integral will diverge or when it will give me 0, okay? And how would that depend on this quantity here? Depends on the sign. So now you start to see that something like that will happen, right? So what do you want? You want to say, actually, let's do it here. We say, well, let's write K0 as R, which is a large parameter, real parameter, e to the I theta, right? So theta, let's try to go from 0 to pi to define this semicircle, okay, that contour. And if this is the case, well, then this is R cosine theta plus I sine theta. And then the exponent will have e to the minus I k0 times x0 minus y0. And therefore, we get e to the minus. So the only relevant part is the real part, right? So I'm going to forget about this one, and I'm going to keep this. This is I with I is minus, and I have a plus, so it's plus R x minus y0 times sine of theta. But sine of theta in this region is positive, so this is a positive number. And now you see that if x0 minus y0 happens to be negative, when I take R to infinity, this contribution will not be there, okay? So if x0 minus y0 is less than 0, my semicircle on the upper half, this integral vanishes as R goes to infinity. And therefore, I can just add 0, close my contour, and then use a contour deformation. Now this is my contour deformation, my full contour. I deform it and only pick up the pole here. When I carry out the integration over the pole there, I get one of these two factors. But that computation was only true when x0 minus y0 was less than 0, okay? if x0 minus y0 is greater than 0, this integration actually diverges. So we cannot possibly use it. We have to use the other one because sine will pick up a different sign. The difference in pronunciation between the two things is a second order effect in my case. So, so forget it. I won't be able to make a distinction. So, but you know what I mean. This guy will flip its sign, and therefore that integration will drop, will be 0. We can close the contour on the lower half, and now pick up this pole, and we will get the second answer. Okay? Very good. Now, this quantity actually has an F here for Feynman. And it has, writing it like this is too long, so people invented a notation for this. There is something called the time operator, the time ordering operator, whose definition is exactly this. If you see anything that has a t in front, what is instructing you to do is to write it as a sum of terms where the operators are time order, and there are Heaviside theta functions or step functions in front, ensuring that they are the only contribution when the time is ordered correctly for them to be the one that you want, okay? So this is something we will encounter many times, but this is the definition. There is nothing fancy about it, okay? Okay. So now we're going to make a radical change of lines of thought. We're actually going to go back to classical mechanics. So any questions so far? Yes?
With respect to this definition of the time ordering operator,
yes.
it only acts on two operators?
No, it can act on any number of operators. So there will be many terms, right?
Okay, but it will be, I mean...
Theta of y0 minus x0 minus z equals 0.
Yeah, you can put many thetas. That's right.
Pardon?
Question?
So you could two combinations of x, y.
So I'm going to use the time to erase as many blackboards as I can while you think. And needless to say, this Feynman propagator will make an appearance many times in the rest of the course.
What's the Feynman propagator?
I said that, well, I should have written it. The F is not for Freddy. I said it. I said it was for Feynman. So this combination, or this, is called the Feynman propagator.
Does this give us a physical reason why we should propose an amplitude of part of propagating from point x to point y? Is it just we're motivated to get to 0?
Well, it was.
I guess another way.
Most times people would just say, well, this is something important, but you see that the way I'm motivating it, it was because it came from unitarity. So it seems to be the object that will ensure unitarity and unitary evolution of your system, okay? So that's part of the reason we did QFT0, just for this very moment.
Was there a physical reason? I first remember it from QFT0. Was there a physical reason why we came up with that object? Or
Yes, it was unitarity. We took S, the S matrix, the S operator. We said it had to be unitary. We wrote S as the identity minus I times the transition operator T, and we imposed unitarity and checked that T had to satisfy some property. And we said that property, we could study it by separating or by introducing a complete set of states in the one particle sector, in the two particle sector, three particle sector, and so on. Of course, we only studied the one particle sector, but you guys were supposed to go on and try this two particle sector, and you all did, I'm sure. But you will, don't worry. It's going to be maybe not in this course, but in the next course. So Tibra might know. In which? Well, no, I shouldn't ask because the answer might be this course. Okay, so we're ready. So back again to classical mechanics. So what did we have there? We had our Lagrangian, right? And we consider variations of this Lagrangian. So this Lagrangian is a functional. Well, actually, the Lagrangian is not a functional. The Lagrangian depends on these functions. It's the action. The action is a functional because it's something that maps functions into the real numbers. The Lagrangian depends on the functions, and it gives us a function, okay? So it's not a functional, but these Q's.
If the Lagrangian is not a functional, then how can you take the functional derivative of the Lagrangian?
Well, that's the point. I'm not taking the, I mean, of course you can take the functional derivative, as we did, right?
Yeah, but
actually, we took the functional derivative of a single function. You remember? That was the first. That was the first thing we did. We took the functional derivative of a single function.
Okay, I thought of that more as a partial derivative.
Well, it's called a functional derivative because this parameter is continuous. Okay, and the answer you get is a delta function, so it's a distribution. It's not a Kronecker delta. Okay. Now imagine that we take the variation of this. So we did it last time. We said the variation of this is this. By using the chain rule. There is a sum over A, right? Now the principle of least action, or the action principle, tells us that we should look at places where the action is stationary, right? And then in order to do that, remember, we had to, first of all, swap these two guys, right? So the first step was to say that this was the variation, the derivative, the time derivative of the variation. And the second step was to integrate by parts. Okay, and we did it very happily. But this time, we are not integrating anything, so we cannot integrate by parts, right? I'm just taking the variation of the Lagrangian. So if I cannot integrate by parts, what do I do? Well, I do the step that comes before integrating, which is simply to say that this thing is minus the derivative with respect to time of this plus this object. this is an identity, right? So you're looking suspicious. What I'm doing is that if you take this guy and you act with this derivative, you can take a derivative on this guy and not act on this, but that cancels this term because this one has a minus sign, and then this guy can act on this, which gives me back what I had from the beginning, okay? All this is just to reproduce the old formula that we wrote down last time. But now I'm being very careful and keeping this term in the equation, okay? Now there is something interesting that I cannot resist to mention, which is that imagine that our Lagrangian didn't depend on time. It didn't have time derivatives. Sorry, it didn't have any time derivatives. So this would be the whole equations. And imagine that the Lagrangian was some polynomial in Q. Therefore, the Euler-Lagrange equations would tell you that the stationary points are just fixed numbers. And there is no dynamics. They are just fixed numbers, okay? So in order to have any dynamics, we really need these time derivatives. But the moment we have derivatives, any kind of derivatives in the Lagrangian, there will be these kind of terms. These terms are unavoidable. You see why? You see that it was the fact that we had these derivatives that when we take the variations will force us to necessarily produce these terms, okay? So they are necessarily there.
Can you repeat that? The thing is...
I really meant to say anything very, very important. All I wanted to say was that these terms are necessarily there, which is obvious from what we're doing. Okay? Now, the second observation I want to make, oh, by the way, the solutions, setting this to 0, give rise to special path, okay? The solutions are called stationary points. Why are called stationary points? That's a weird name. They are called points because they are points in the space of possible functions, right? So if you imagine a big space where each point corresponds to a function, the solutions to this equation are points in that space, and they are called the stationary points of this Lagrangian, or sorry, of the action constructed from this Lagrangian, okay? It's not supposed to, okay. Just stay there. Good. Okay. Now, let's imagine that we have, say, in T, and our space of coordinates Q. Say we have some T1 and some T2 time, right? And we have some path, any path, that goes from here to there. So this we would call Q of T is a function, okay, that describes some configuration here and some configuration here and how it moves in time, okay? Now I'm going to take this guy to be any path or any function, okay? Not necessarily a stationary point, okay? It's any function. Now imagine that if I have this function and I add to it a little bit, I mean, it could actually go down, but since I only have one color, it's going to be up all the time. Are there more colors? It's funny, but they disappeared. There were yesterday. But it doesn't matter. We can always make it like that. Okay, so imagine there is, yes. Oh, that's great. Thanks. Now we know what happens to the color chalks. Okay, but it's too late to draw it going down. So we have this other path. Let's call this one Q prime of t. Now Q prime of t is obtained from Q of t by some special variation. So this variation is actually something that I design, that I add at each time to my function Q so that I produce Q prime. Okay? Yes? I should in principle. Yes. I could keep the points fixed, but I'm not going to worry about that here. So imagine that we have something that does this. Now, imagine that there exists one variation, so I'm going to call it hat, that does something very, very special, okay? Has nothing to do with the function to which this guy is applied. So it's something that you can apply to any function, okay? Any path you have, you add these guys and you produce a new guy so that your Lagrangian as a function of Q actually remains invariant. Okay? Imagine that there exists a variation such that the Lagrangian is invariant. Okay?
So here the variation is special rather than the path itself.
Yes, so we're doing something for any path. And all it happens is that if you evaluate the Lagrangian on this path and evaluate it on a path that is deformed from this one by this special, very tailored design variation, then the Lagrangian is invariant. Okay? What can we conclude from here? That is one logical, yes. That is definitely a logical conclusion, yes. But I mean from the things that we have on the board, right? So if we combine 1 and 2, okay, combining 1 and 2, we see that the statement that this is an invariance, actually, people would call this a symmetry. A symmetry of the Lagrangian is a statement that this variation will be 0, the special variation, right? But if this variation is 0, well, I can apply it to the variation that I had over there, right? And then I'll find that, of course, this calculation that I did there was for any variation. So I'll have this, and then I'll have this, Q dot A, delta hat of QA, and then this total derivative of what I'm going to have is going to be Q dot A, Q hat of A, right? So that was true for any variation, in particular for our fancy variation. But now this is telling us that this quantity has to be 0, right? Now, what happens if on top of everything we're doing, we say that our functions now, the functions Q, happen to be stationary points. What do we conclude? Then this is 0. So we conclude that this has to be 0. Isn't that amusing? We found a quantity that is constant in time. So how can we call such a thing? Well, it should be called a conserved quantity. Following, following your logic, this should be called a conserved quantity. Conserved quantity meaning that on the dynamics of your system, the time derivative is 0. So once you fix this at some time, then it's going to remain the same at any later times. Yes?
So you're calling this a symmetry because it gives you a Lagrangian invariant, right? But
that's right.
why should we consider just the Lagrangian remains invariant under this symmetry transformation and not the action, which is the thing that will give you the equations of motion?
Very good. We're going to generalize this soon enough. So, in fact, asymmetry, as you're saying, all it has to do is to leave the action invariant. And therefore, in the case of classical mechanics, this could be a total derivative. Okay? If it's a total derivative, we're still fine, no problem. And then, this would be a total derivative with respect to time. This will still vanish. And these two quantities will combine to give us our conserved quantity. Okay?
So you're assuming that such a variation that these Lagrangian invariants exist. So that's an assumption because I mean a priori the Lagrangian and the curve might be.
Yes, of course. If there are none, so your job every time somebody gives you a Lagrangian is to look like crazy for anything that does this. Sometimes you won't find any.
Yeah, that can happen.
Why doesn't it need to be problem? Why can't it be just a no function?
Sorry, why does he have to?
Why doesn't the change in why can't it be just a no function? Then
Well, I mean, no, of course, this is going to be equal to this for any function.
Yes. So of course.
But then it means that this quantity is not conserved in time. I mean, first of all, for any function, this quantity is not conserved. It's not going to be conserved in time. It's going to be equal to this. But we don't really care about them, at least not in classical mechanics, the ones that don't satisfy this, right? So we only are interested in the ones that satisfy this equal to 0. And for those, this object happens to be conserved in time.
What I'm asking is why does delta L have to be 0?
Yeah, it doesn't have to be 0. It could be, all it has to be is a total derivative in time of something, which you can call f. Because as Andres said, all we need is the variation to leave the action invariant. And a total derivative will not affect the action. And then when we put it here, the full statement would be that this minus f is the conserved quantity. Okay? So if you include this, you will have to put it in here. And that will be the conserved quantity. But we're going to do it for classical field theory.
So we know that Lagrangian is not uniquely defined, right?
Yes.
Lagrangian. So can I just like build conserved quantities however I want? I mean, just by requiring that this is satisfied, or just the conserved quantities should pop up from my physical system?
No, just you should try, right? You should try to see. It's not going to be trivial. You have to find something whose variation of the full Lagrangian is a total derivative, or it's 0, right? So it's not a trivial statement, right? So let's do an example. This is for exercise. So take this Lagrangian. It's a Lagrangian where our coordinates are x and y, okay? And our Lagrangian is x dot squared plus y dot squared minus some constant x squared plus y squared. Well, I'm sure you all have done something like this sometime in high school. If you went to a good high school. Not mine, I didn't do this in high school. But in any case, we're going to do it in a slightly different way, just because it's going to help you out next week. So we're going to do it by introducing different coordinates. We're going to do it by introducing z and z star as our variables. So in terms of them, the Lagrangian is now simply z dot times z star dot minus a z times z star dot. Okay? Very good. The stationary points are what? Well, if we perform the variations, okay, the variation that is proportional to z, so you don't like complex variables? Or?
No. Because this is a function of both z and z star, so this would be non-analytic.
Well, something non-analytic is something real. And I have to tell you that this was a real object.
Pardon?
This was a real object.
Yeah.
Yes. So it's not surprised that we didn't get something analytic. Right? So let me give you an example. I'll give you an example. Take the function x, f of x equals to x, right? Is this function analytic? Exactly. Do we worry that this function is not analytic? Well, it depends on the purpose, but I wouldn't worry so much, right? In fact, you live all your life doing things like this, and you didn't worry that there wasn't any complex structure behind, right? Well, so let's take the variation with respect to z. So what do we get? We get something that looks like z dot dot star minus a z star. And the variation with respect to z star will give us minus z dot dot minus a z. So those are the equations. The stationary points are points where this is true. Okay? Now, I told you, right, and you all, I'm sure, were trying, that every time somebody gives you a Lagrangian, you should try like crazy to find symmetries of the Lagrangian. Did you find already one symmetry of this Lagrangian? Exactly, by a phase transformation. Where is the... They are all up there. So they are all, this thing is invariant under a phase transformation. So a symmetry is the following. Take z to be e to the I theta z, and z star to go to e to the I theta z star with a minus sign. This is a transformation that leaves the Lagrangian invariant. Now, this is actually, these symmetry transformations, we can apply several of them, and they actually form a group, okay? And this group has a name. It's called U1, okay? Because it's a group of unitary matrices of 1 by 1.
Theta is independent of T.
Yes, theta is independent of T. This is called a global transformation. But
so this, in this case, a question. It should be also, I mean, if I make it dependent of T.
It will not be a symmetry.
Oh, why not?
Well, try.
That's not okay, so it's not working.
I mean, you will get another term, right?
Okay,
You have to apply the derivative on the function and on the phase factor. But that's a very good question. You can ask, can we make global symmetries? Global means that I have to do it to the function. I have to do the same thing to the function everywhere. So here, I'm shifting the function by the same amount everywhere. That's called global. There is another possibility, which is a local transformation, something that actually depends on the position. Okay? So you could ask, are there such things, and are they useful? Yes?
If we have to do the same move at the same amount, independent of time, how can we do that without, while still having the ends fixed? Surely that means
I said I'm not fixing the
not
end.
fixing the end.
That's something we keep in mind from high school. Here, I'm thinking about functions that die off at minus and plus infinity. So if something dies off at plus and minus infinity and I add up something slightly to it, it still dies. Very good. So let's do this. Now, if we have something like this that depends on a parameter, on a continuous parameter, in this case theta, we can take it to be infinitesimal. So if we take it to be infinitesimal, then the variation that we have to add at every point for the function z is nothing but I theta times z, right? Now, the variation, what I'm doing is expanding this, imagining that theta is very, very small. So I have 1 plus I theta, okay? So the difference between the new one and the old one happens to be I theta times this guy. So we have this guy and this one for z star, okay? Now this is our new fancy variation, okay? A special variation. This is a delta hat that I was using here. From here, we know that this thing, the Lagrangian, if we compute this variation, we're going to get 0. So everything we said should apply. So can we derive what our conserved quantity is in this case? So let's compute Q. So what is Q? Well, I'm supposed to, in order to compute it, I'm supposed to compute this quantity, the derivative with respect to z dot, the variation, the fancy variation on z, okay, plus z star, the variation on z star, okay? I'm summing over A, okay? So A is the index that tells me the different objects, the different functions I have, the different coordinates. In this case, there is z and z star. So when I compute this, what do I get? This quantity gives me z star dot times this, which is this object. So I get z, and I'm going to pull out a factor of I theta. Okay. When I do this one, I get minus, because there is a minus here, z dot z star. So we can forget about this. This is not important. This is just a parameter. So the quantity that is conserved in time is this. Okay? If you don't believe me, use the equations of motion and check that Q dot is actually 0. This should be, well, it's actually, you can just do it. I can give you 10 seconds to do it. Use the equations that are somewhere there, here, and check that it's 0. If it's not 0, don't tell me now. You can tell me after the lecture, and then we can discuss why it's not 0. No, but it should be 0, unless I made some mistake. Yes? Any questions?
In that step, those 2 lines there, I don't know where these what they were.
They are these. Okay. Now we're world experts in symmetries in classical mechanics. So what's the next step? We go to classical field theory. Yes?
One question. So you get rid of the theta in that expression, right?
Because it's a number. It's a fixed parameter, right?
Right. So in case that, for example, theta depended on G.
Which we are not discussing.
Right. Okay.
And in this case, it's not a symmetry.
All right.
So what's your point?
The point is that you can always get rid of the parameter of your transformation in this way.
Yes.
Other question. What if this was like a discrete thing?
Yeah, if it's a discrete transformation, then we're out of luck, right? Because we cannot have an infinitesimal variation. The transformation doesn't belong to the set of variations of the Lagrangian. So the whole argument breaks down. So there are no conserved quantities as connected to discrete symmetries. Well, still back to now classical field theory.
Sorry, did you say that there are no conserved quantities with discrete symmetries?
Associated to discrete symmetries. Well, in fact, so we just realized something very important, which is what we're saying, right? That every time there is a continuous symmetry, a continuous global symmetry, there is a conserved quantity. That statement is actually not quite true. And remind me, if I didn't tell you why it's not quite true, remind me that it shouldn't be true in general. So remind me at some point, if I didn't say it. Okay, so do we have time for that, or we don't have time? I think we have time, right? So there is we still have 10 more minutes, right? No, but we started at 3:40. We're supposed to finish at 5:10 formally, and I can always take 10 more minutes. So in fact, we have 15 minutes. So what does the theorem says? Well, I'm not going to tell you what the theorem says right now. Let's actually work it out from the Lagrangian. So now we have a Lagrangian density. Okay. Would you mind closing the door, please? It's a little bit annoying. I don't know what they are doing. It's at this time.
It's like Darth Vader.
Yeah, that's the. Okay, so just like last time, we're going to look at the variations of the Lagrangian density, and we're going to get the usual terms, sum over I, and then we're going to get the usual term, right? So the next one, yeah, maybe let's do it carefully. So we have the variation of this guy. Just as in classical mechanics, last time we showed that this was the derivative of the variation. And once again, we're not going to drop out anything because we're actually looking at the Lagrangian density, not the action. So we have to rewrite this as minus the derivative with respect to phi of times the variation plus the total derivative term okay? Yeah, there is a conspiracy somehow. Okay. So, second thing is that we imagine there is our super fancy transformation, delta hat, that does the following. In order to make happy everybody, we're not going to assume that the transformation is actually leaving the Lagrangian invariant, but we're going to assume there is a total derivative of some object, which I'm going to call f. I mean, I think people call it f. Yes. Okay, so delta is called a symmetry. If this happens, because the action doesn't change. Once again, this thing depends on the field.
Not on the derivatives?
It could depend on the derivatives, yes. Yes.
When you say the action doesn't change, do you just mean you're just shifting the action by a constant? Or
No, here the action doesn't actually change because I'm assuming that all the fields die at infinity. So when we have an integral d for x of something that is a total derivative or a divergence, we can use Stokes' theorem and rewrite this as an integral over a boundary term, which happens to be at infinity. And I'm assuming that all these fields die fast enough at infinity so that there is nothing there. Yes.
More for the first lecture, but it's relevant. When we write out the Lagrangian, we write it as a function of q and q dot. But in the Lagrangian formalism, we really specify the endpoints. So q dots are sort of, aren't they redundant in that case? I mean, q dots depend on q.
Well, once again, we are not fixing any points, right? I mean, it's probably, yeah. So, as I said, once again, we're imagining, we're doing everything from minus infinity to infinity, and our fields or our functions die at infinity. Fast enough so that we don't worry about boundary terms. Okay? So now we have this. Applying the same idea, combining 1 and 2 together, then implies that this thing has to be equal. So at the stationary points, this thing has to be equal to that quantity over there. Okay? And therefore, this quantity just as before, vanishes. And this is going to be the relevant quantity for us. And it's called a conserved current. Well, it's a current because it's actually a vector. Yes.
So we're defining that conserved current in terms of being the divergent list, right? So I can also add to that current, for example, the derivative of an anti-symmetric tensor, and my current will be shifted, right? Because it also satisfies the.
Yeah, you can add to the current anything that is that.
I mean, it's not uniquely defined.
You can add, yes, you can add to the current anything that is killed by this operator, right? But that's not very interesting, right?
I mean, because if I want to calculate things with the current, then it will depend whether I have an extra term or not, right? And
in other words, imagine there is nothing. I mean, you just construct any random object. Say you put here pi. Is that something very interesting? Say pi is conserved. It's a conserved current. And you learn physics from saying that pi is a conserved current. Sure enough, it's a conserved quantity. But it's not something that you can learn from it. You need to construct a function that depends on your field configuration and happens to be divergentless.
right.
Well, how do you do it? It's very hard. I'm telling you how to do it. I mean, if you have any other way of constructing functions of the field such that they are divergentless when evaluated at stationary points, that would be spectacular. Let's just say that. Okay? So far, this is the most powerful way we have to do that. Okay? And this is the theorem. The theorem says that every time you have a continuous symmetry, you have a conserved current. Okay? The theorem doesn't say that you have a conserved charge. Okay? That's something we add to the theorem, which is not always true. Okay? So the theorem ends here. And then sometimes that it sees a conserved charge. Sometimes, actually, I should say, most of the times, that it sees a conserved current. Why is that? Well, if you take the zeroth component of the conserved current, okay, and you integrate over space, if this converges, and here is a catch, not always that integral is convergent, but if this converges, then you call it Q. Okay? Otherwise, it wouldn't make sense to call it anything. So you call it Q if this converges. And when this converges, this is a conserved charge. Why is a conserved charge? Well, take the total derivative with respect to time. After all, this only depends on time. You're integrating a space out. Okay? Take the derivative with respect to time. When you put it inside this, is a partial derivative of the object, but this was a conserved current, so this is minus the integral d3x. The divergence of the space components of the current, and this thing is a boundary term which again vanishes by our assumptions that the field die off at infinity, but they are actually equivalent to the fact that this guy exists, okay? So we get a conserved current in this case, okay? So I want to end with an example for which we have 4 minutes. No, maybe not. Yeah, this is something that has to be done in more than 4 minutes. Yeah, I don't think we can. Yeah, so let's stop here. Let's do the example tomorrow. Yes?
So previously when you wrote down the Feynman propagator, you motivated from Q to 0.
Yes.
Where the Conofield theory presumably was not interactive. Whereas the Conofield theory that we were considering today didn't have any interaction term. So the two M's, could they be the same M or?
Oh, the M's.
Right. Or
well, it depends. If you remember, we were talking about the 3 approximations.
Right.
In that case, it's the same M. Yeah, well, I don't expect you to remember everything from the QFT0, but at the time, I introduced a rational function approximation, something that is, I just made it up. But in that approximation, the m is the same as the m that we have. Well, I made it up at the time, yes, but it's true. Okay.